So in this part now, we're going to look at some basic properties of the logarithm. We'll go a lot more into this in the next section, but a few of the properties I just want to point out. What I did point out through the definition, if you remember, is that whether the base, is positive, whether the base is greater than 1 or positive and less than 1, in either case, you're going to have this. The domain is all positive real numbers, and the range is all real numbers. It does actually follow from the definition. I did mention it. You can also see it from the graph, actually. I will show the graph for the cases when a is greater than 1 and when a is positive and less than 1. From my experience, though, studying math, the case when a is greater than 1 is really the more important one. But this is when a is greater than 1. You can see here that this function is only defined for positive numbers. As you can see, it never crosses the y-axis. Remember, the y-axis is the vertical axis. It never crosses that. And not only that, the function is not defined for negative x. Okay? As you can see here, it does intersect the x-axis once. It turns out it intersects it at 1. In other words, the only x-intercept for the logarithm is at 1. And we'll see why in the next section. It's actually really not that hard. It just follows directly from the definition. Okay. What I should say here also is if you notice, I know it's kind of hard to see it from the graph. What I will do is post some kind of Desmos activity or something that'll help illustrate it, probably just calculation based. But as you can see, hopefully you can see from here though, that as your x is positive, but if you let x get closer and closer to 0, but never actually get to 0, the function gets more and more negative. That's why in this case we say x equals 0 is a vertical asymptote. This is the case when a is positive but less than 1. It is very similar in that it has the same domain, the same range. It actually has the same x-intercept, meaning it crosses the x-axis at 1. But here you can see, though, the end behavior is actually going to be very different. Whereas in the previous case here, if you let x get bigger and bigger and bigger, the function values get bigger and bigger and bigger as well, without bound. And not only that, this function is increasing. Whereas in the case when a is positive but less than 1, the function is decreasing. And these are just some of the facts that I pointed out. Again, here's the domain and range. The x-intercept, as I said, is 1. In other words, this is really saying that if you do log base a of 1, you're going to have to get 0. And again, that really just follows from the definition. You could just do a log roll, because if you do a to the 0, you're going to get 1. That's why. So a to the 0 is in fact equal to 1. So that's really why it's true. We also, as I said, the y-axis is the only vertical asymptote. Basically, as x approaches 0, but x is always positive, but we let x get closer and closer to 0, the logarithm function is either going to go to plus infinity or minus infinity. In either case, we say it's a vertical asymptote, and there's no horizontal asymptote. We have these 3 points that the graph must pass through. Again, they just follow directly from the definition. You probably have saw it already. Those graphs have no breaks in them. In other words, you could draw the graphs without having to lift your pen or pencil off the paper. In other words, these functions are continuous. The functions now, that's what should be functions, these are continuous. And as we said already, the function's increasing when a is greater than 1. It's decreasing when a is positive, but less than 1. Okay, so we have that. We also have this result. This actually comes up when we're finding the domain. If we have, again, a is positive and less than 1. What we can actually do is we could do the logarithm of some other function. We could do the logarithm of another function. I'm calling that inside function g of x here. And you could consider, well, what would the domain of this whole thing be? It turns out to be all numbers x in the domain of g such that g of x is positive. Again, we did skip over composition for time consideration. That's really what this actually is. But I still wanted to go through this a bit. But again, when you do logarithm of something in terms of x, the domain of this new function, it's all elements in the domain of the inside function. I'm calling that g of x, but such that g of x is positive. So in particular, if g of x was something like a polynomial whose domain was everything, all we care about is when g of x is positive. That's really what I'm trying to say over here. I will do some examples of this. All you care about is all x, where the inside here is defined, what the domain is, and such that the inside is positive. As an example, let's consider x plus 8. Well, x plus 8 alone is defined everywhere. So we want to know, when is x plus 8 positive? Let me say that again. So we know that x plus 8 is defined everywhere. So in that case, all we care about is when the inside is positive. Well, this is positive only when x is greater than negative 8. Sorry, that's a typo. That's when x is greater than negative 8. So that tells us the domain is all x greater than negative 8, which is the same as this interval. Okay. Here's another example. 5x plus 4, right? This is defined everywhere. So we have that. See if I can fit it. Almost. So all we care about then is when the inside is greater than 0. Again, it's defined everywhere. Let me actually just fix that a bit. Let me just write it out. Defined everywhere. So its domain is all numbers. So all we care about then is when 5x plus 4 is positive. But again, that's just solving an inequality. So we subtract 4, we get 5x greater than negative 4. Divide both sides by 5. These cancel. We get x is bigger than negative 4 over 5. So the domain for f then is given by this, which is the same as saying negative 4 over 5, comma, infinity. Here's another one. Yes, we do have a plus 3 here, but really all we care about, is the x plus 4. Well, again, x plus 4, this is actually a polynomial of degree 1. So this is defined everywhere. So we want to know then, when is x plus 4 greater than 0? Well, again, just like the above, we're going to solve this inequality. We subtract 4. We get x is greater than minus 4. So in this case, the domain is minus 4 to infinity.